Okay, it looks like we're at a pretty stable number. So welcome everyone to the January 23rd Biocurator Working Group call. Today we're going to hear from Ozge and Ryan about updates in the congenital myopathies expert panels. Ozge will talk about the gene curation expert panel and Ryan will talk about the variant curation expert panel. As far as announcements, we are going to have a question and answer session on gene curation in the next Biocurator Working Group meeting on February 12th. And so we would love to hear from you about what questions that you have when you curate gene disease relationships. And so we put together just a little brief Google form. So if you have any questions, please do fill that in because it really helps us to set content for this meeting instead of just coming with a bunch of random content. So we encourage you to ask questions for that. And then with that, I will turn it over to you, Ozge, and thanks for coming and presenting.
Of course, I'm happy to join you guys. Let me share my screen. And presentation. Okay, can you guys see my presentation?
Yes.
Okay, great. Hi everyone. I'm one of the co-chairs of the Congenital Myopathies and Myasthenic Syndromes GCEP, and also the VCEP. We used to be called only the Congenital Myopathies Group. And we started as the congenital myopathies group, but then later on we added congenital myasthenic syndromes to our scope as well. So our GCEP was first approved in October 2019. So we've been working on gene curation for several years now. We have a group of experts, including genetic counselors, molecular geneticists, clinical geneticists, neurologists, and doctors, researchers, physicians, and people from commercial laboratories. So we are a very diverse group. And it's a very international group. We have experts from many different countries, including United States, Canada, United Kingdom, France, Italy, Estonia, Finland, Japan, and Australia. So in our meetings, we have people joining from, on the other side of the world, just, it's nighttime in their time, but they are very enthusiastic in joining us in our bi-weekly meetings. So I'm a co-chair. So the other co-chair of our group is Dr. Karsten Bonneman at the NIH, and our coordinator is Emma. So I just want to give a brief introduction about what congenital myopathies are. So we started with congenital myopathies, and we've spent most of our time curating congenital myopathy genes. So I will mostly be talking about that. So congenital myopathies are a group of rare neuromuscular disorders. So rare, the estimated prevalence is about 1 to 5 in about 100,000 births. So they are really extremely rare. They typically present at birth with hypotonia and muscle weakness, but it's a very heterogeneous phenotype. So patients may also present later on in life with weakness. Or in utero sometimes. There is a really kind of wide range of presentations. They may also have respiratory insufficiency, feeding difficulties, again, because of the underlying muscle weakness. Cardiac muscle involvement and cardiomyopathy is rare, but it can happen in certain forms. They tend to be non-progressive. So what really differentiates congenital myopathies from muscular dystrophies, which are also neuromuscular disorders, is that congenital myopathies tend to be non-progressive or slowly progressive. And they don't involve continuous degeneration and regeneration in the muscle, which is what you observe in muscular dystrophies. So dystrophies tend to be progressive diseases. So congenital myopathies are defined by certain characteristic structural changes in the skeletal muscle, which is also called their histotypes. So these are specific things that you observed in the muscle biopsies, which really forms the basis for their subclassification as well. So for instance, the presence of these structures called nemaline rods that we observe in nemaline myopathy, the observation of the nuclei in the center of the muscle fiber that you observe in centronuclear myopathy. Normally, you see the nucleus more towards kind of like the corner in a section of the muscle biopsy. Or, seeing these cores, these, lack of staining in central core disease. So patients in the past, before genetic testing became so widely available, were being diagnosed based on these characteristic changes in their muscle biopsies. And pretty much every patient had to receive a muscle biopsy to have a diagnosis. But that's changing rapidly with the take on of genetic testing. And sometimes patients may not even need a muscle biopsy now if they receive a genetic test and they, if you identify a diagnostic mutation, then they may already have a diagnosis. So far we have completed the clinical validity assessment of 49 gene disease pairs for 37 genes associated with congenital myopathy. So when we first started, we made our list of genes that have ever been associated with congenital myopathies. That was 37 genes. I have to say, since the time we started, it's been about 5 years. There have been a few additional genes reported, and our aim is to get to them, at some point as well. And some genes were associated with more than one disease that was still under the umbrella of congenital myopathy. So we ended up curating 49 gene disease pairs. 13 of these genes were related to a broad histotype spectrum that encompassed 2 or more histological features. So we spent a lot of our time actually in our GCEP meetings to decide whether certain presentations should be lumped into one disease entity or should be, split into different disease entities. But we ended up, lumping some of them because of the continuous, phenotypic spectrum. So for instance, for ACTA1, we ended up calling the disease ACTA1 related myopathy, even though there are different types of presentations that can be associated with ACTA1, that can be Nemelin myopathy, central core disease, etc. So it can be like a wide range. 10 of these genes were associated with diseases that encompass both autosomal dominant and autosomal recessive inheritance. So again, some of these were curated separately for autosomal dominant and autosomal recessive inheritance. 8 genes were associated with Nemelin myopathy. That was the most kind of common diagnosis. And 6 genes were associated with centronuclear myopathy. So that was the second most common disease. So for our gene curation process, this should be, I'm sure, similar to many other disease areas. So we had either an expedited curation process or a standard curation that was, more detailed. So if the gene disease, if there was abundant evidence and the experts agreed that, okay, this should be kind of a straightforward curation, we followed the expedited curation process. So gene disease relationship was assigned to 1 biocurator and 2 experts. And, I think you guys must be familiar with the expedited curation process in this group. Or, if there was less abundant evidence and there were conflicting opinions, we thought that it would take more time to take a look. We followed the standard curation process. So for congenital myopathies, we needed our biocurators to be really familiar with the different presentations that are observed in the patients. So we gave them this kind of guidance documents to ask for them to specifically look at certain features in the papers, such as muscle strength, ambulatory status, facial weakness, the presence of high arched palate that can indicate muscle weakness in utero, respiratory difficulty, ocular involvement, cardiac involvement, scoliosis, etc. So these are all features that will that really help our experts when they are reviewing the evidence determine whether the patient indeed met criteria for a congenital myopathy and which type of congenital myopathy. In addition to that, certain muscle biopsy findings were really critical for us to take a note of. So such as, was there centralized nuclei? Was there fiber size variation, fiber type disproportion? Were there any cores or aggregations defined in the biopsies? Because these were really important, again, to decide whether we would count a patient as genetic evidence or not. So I have to really acknowledge all of our biocurators in this process. We've had many biocurators who helped us and worked with us over the years. Our lead biocurator has been Justin, who has been really amazing. And we've had, some members who are still with us and, some people who also have moved on. So overall, in these 49 gene disease pairs, we had 35 of them, so 71.4%, having a definitive classification for we had 7 genes, so 14.3% having moderate, 6 of them, 12.2% having limited, and we had 1 gene that had disputed evidence for their association with disease. So when we look more in detail, we had 12 genes that reached the score of the maximum 18. We had genetic evidence reaching 12 points in 28, so 80% of the definitive classifications, and overall 57.1% of all classifications. The experimental evidence reached the maximum 6 points in 14, which is 40% of the definitive classifications and 28.6% of all classifications. And I just want to point out some points here, some of the genes, if I can let me move this my screen here. So let me point out. So 5 of these genes that had definitive evidence, RYR1, Nebulin, MTM1, Dynamin2, and ACTA1, we selected to prioritize for our variant curations. And talk more about our VCEP after me. So these were the 5 genes that we thought are really well-established disease genes and have many variants reported. And we thought it's really critical to prioritize them for our VCEP so that they would be the most useful as a start for laboratories and clinicians to have our expert-approved variant classifications for. And we had some genes that are associated with other phenotypes other than congenital myopathies. And there are some other expert groups in ClinGen who specifically work on those associations. So one example of that is RYR1. So RYR1 is associated with congenital myopathies, but also malignant hyperthermia. And there is a ClinGen malignant hyperthermia expert group who has been defining the criteria and has been doing variant curation for that phenotype specifically. But we are focusing on its variants that are associated with congenital myopathies only. And we, again, focused our gene curation for its association with the congenital myopathy phenotype. So that was one example of that. CDC 78, just want to point this out as an interesting example, a total score of 7 points, which would have been sufficient for moderate classification, but there were only 2 probands available to be scored as genetic evidence. The rest of the evidence was coming from experimental evidence, so it remained as having limited evidence because it didn't reach 3 probands. We had 6 genes that had limited evidence overall and 6 other genes, and 4 of these were implicated in multiple diseases. So for other diseases, they may have been classified as having a higher level of, evidence, but for these specific diseases, they had only limited evidence, and these are BIN1 associated with autosomal dominant centronuclear myopathy, TNNT3 associated with autosomal recessive myopathy, TNNT1 associated with autosomal dominant myopathy, and COL6A3 associated with autosomal recessive dystonia. And we had one gene, RYR3, that has been reported in patients with congenital myopathies, but when our experts panel reviewed this gene, we decided that the evidence has been disputed for its clinical validity. So we then looked at, so this is for our manuscript that we are, that's currently under review for our GCEP work. We basically wanted to see how our gene disease relationship assessments may impact our variant classifications for congenital myopathies. And for that, we looked in ClinVar classifications for variants in these genes that have been classified as benign or likely benign, that have not been classified as benign or likely benign. And we looked at the ratio of variants that reached a pathogenic or likely pathogenic classifications versus those that were still VUS. So in genes with non-definitive classification, only 5.7% of the variants, other than those classified as benign or likely benign, were classified as pathogenic or likely pathogenic, whereas 94.3% were classified as VUS. But in genes with a definitive classification, 22.6% of variants other than those classified as benign or likely benign were classified as pathogenic or likely pathogenic, and 77.4% were classified as VUS, suggesting that our curation, genes that don't have a definitive classification yet have more VUSs in them, which increases the uncertainty for clinicians who basically receive these reports and then have to follow up on those VUSs. So our gene curation process definitely, I think, helps clinicians understand, the clinical significance of their variants better. So just want to briefly mention the congenital myasthenic syndrome genes. We just started working on them just a few months ago. We expanded our scope. We included additional experts who have more specific expertise in congenital myasthenic syndromes. So congenital myasthenic syndrome is again a neuromuscular disease, but it is a disease that results from defects in the neuromuscular junction, as opposed to congenital myopathies, which result from defects that are specifically in muscle proteins. So again, this is a heterogeneous disorder. It has genetic heterogeneity, and it really encompasses a group of disorders that have wide phenotypic presentations as well. So we have 36 genes that we initially listed for for curating for their association, for their congenital myasthenic syndrome association. So we are just starting to work on these. I think curated single gene, only one gene so far, but we are working through them. I think that's all I have. I'm gonna stop sharing so Ryan can go.
Great, thanks, Ozge. We'll hold questions for both of you until the end and pass it over to you, Ryan.
Great, thank you. I'll go ahead and share my screen. Hopefully everyone can see my slides. I'll be covering the VCEP for the congenital myopathies expert panels. Thank you, Ozge, to the great introduction with the GCEP. Covering again some of the background information that Ozge did a great job of describing. Congenital myopathies are a group of neuromuscular disorders that I'm making sure. Okay, I thought I was muted still for a moment. That typically present at birth with hypotonia and muscle weakness, with an estimated prevalence of anywhere between 1 to 5 of 100,000 live births. And as of 2020, there were 33 genes described as having definitive evidence for a causal role in disease by the Congenital Myopathies GCEP. And of those 33 genes that had a definitive classification at the time, the Congenital Myopathies VCEP, as Ozge mentioned, defined criteria for variant classification in the 5 genes with pathogenic variants most frequently reported in congenital myopathies patients. Those again are ACTA1, Nebulin, MTM1, DNM2, and RYR1. Each of these genes have up to several hundred variants reported in patients with varying amounts of data and literature supporting their association with disease, which poses a challenge in the clinical setting. And ClinGen ultimately assembled a group of experts to form the ClinGen Congenital Myopathies VCEP in October of 2020 to do the following, including define criteria for the specification of variants related to congenital myopathies based on the ACMG AMP criteria, also to review variants that have been reported in association with these disorders, and finally provide expert-approved classifications for their clinical significance, which are ultimately posted publicly within ClinVar. As far as membership goes, there are 36 members in the VCEP spanning 9 countries, as can be seen in the map in the upper right-hand corner of this slide. The chairs of the VCEP, similar to the GCEP, are Ozge, who you all just met, and Karsten Bonneman, and the coordinators are myself as well as Marina Di Stefano. There are 24 experts on the VCEP as well as 8 biocurators, some of whom are staff biocurators with ClinGen, and a number of them are also volunteers. So we have a number of helping hands, which makes curation progress much easier. As far as the VCEP's progress goes, again, the VCEP was initiated in October of 2020, where the definition and scope was defined. Then in July of that same year, we began to draft and specify the ACMG AMP criteria in regard to the 5 genes that we've been reviewing. And as of August 2024, we've finally finished and have received approval of the pilot variants for those 5 genes that we've reviewed. And so currently we are in a phase of sustained curation. And over the next few slides, I'll be discussing both how we went about specifying our criteria for those 5 genes, as well as some of the results for the pilot variants, of which there were 87, and then also where we're currently at with sustained curation. The congenital myopathies VCEP's approved specifications are available in the criteria specification website, the CSpec, at this given link, which I'll also post in the chat following the end of these slides during the questions section. There are 7 documents, 2 for ACTA1, 1 for dominant and 1 for recessive inheritance, 2 for RYR1, again, 1 for dominant and 1 for recessive inheritance, and then 1 document for Nebulin, DNM2, and MTM1, and 86 variants are currently live within ClinVar. As far as specification challenges that we encountered during our pilot round and specifying the ACMG AMP criteria, as mentioned before and during Ozge's presentation, congenital myopathies are rare, which affected how we wanted to ultimately handle case counting for PS4 and PM3. To address that, we ultimately, with slightly fewer cases than are based on the general SVI recommendations. If those cases are well phenotyped, we can generally reach a higher score for the criteria that we've set because these cases are so rare, especially those that are published and publicly available. The gold standard for phenotypic diagnostics is a muscle biopsy, as Ozge demonstrated on one of her slides, which is becoming less and less favored because of its invasiveness. And even when it is performed, results are not always given to the lab where testing is ordered. And so that posed a challenge for PP4, the specific phenotype code, as we wanted to include that. But there were cases where we did not have that specific information, which made that criteria difficult to specify in regard to this clinical domain. There are also many functional assays out there across all of these genes because many of these genes are molecular motors, which posed a lot of literature to sort through and verify the quality of each of these functional assays. So this led to a bit of a pipeline challenge with specifying PS3 and also needing to exclude, in some cases, BS3 for some of these genes due to the numerous possible functions of some of these proteins. Finally, there were some genes with multiple mechanisms of, or modes of inheritance, those being ACTA1 and RYR1, and there are missense variants, which we were reviewing without informative literature. And so handling the classification of those variants sometimes posed a challenge where we had to specify which thresholds for PM2 supporting BA1 and BS1 to use, and in those cases, whether or not the variant was a missense variant versus a loss of function variant that potentially is eligible for PVS1 was sometimes indicative of which path to choose. Getting into some of the specific choices that were made, these are all of the PP4 approved phenotypes for the autosomal dominant specifications that we've established. Without getting into the weeds of each of the criteria that's looked for across each of these gene-disease relationships, as you can see emboldened in each specific category for each gene-disease relationship, muscle biopsy was one of the key features that we look for, which are specific to these gene-disease relationships. And while there are, in some cases, alternative phenotypes that we can look for that are specific to disease, such as the case for RYR1, where in autosomal recessive patients, we can look for exercise, heat, and aesthetic-induced rhabdomyolysis, as well as ophthalmoplegia, excuse me. But in many of these cases, we do look at muscle biopsy, which in some of the reported probands are, again, absent, which poses a challenge. Additionally, looking at the approved functional assays, as described earlier, because many of these are molecular motors, these genes that we've reviewed, there were multiple functional assays available for each of these genes. As you can see in the functional assay column, we have those various functional assays listed with 3 for ACTA1, 2 for DNM2 approved, 5 being approved for MTM1, 2 being approved for Nebulin, and 3 being approved for RYR1. And this is just a handful of the total assays that we actually ended up reviewing in total, and we gave a proposed strength for any one of these assays being PS3 supporting. But the VCEP has also approved uniquely stacking of these assays to increase the strength of PS3, such that if there are multiple unique assays for any variant in one of these genes, we can potentially upgrade the strength of PS3 supporting to something like PS3 moderate or strong. And additionally, lack of effect in a specific or specified assay does not count towards benign functional evidence or BS3 codes in multiple cases based on, again, the wide range of functions of some of these genes and the proteins they encode. And additionally, animal models of specific variants in all genes are reviewed and assigned an appropriate strength of evidence on a case-by-case basis along the PS3 supporting to PS3 strong spectrum. And finally, because there were so many of these assays that the experts were able to approve based on quality and quantity within the literature, some of these do have an asterisk next to their title, and that's because these assays should not be stacked to increase the strength of PS3 supporting because they may be assessing or not be rather assessing independent biological functions. So that was how we tackled PS3 and the, again, wide range of potential functional assays that were in the literature for a lot of these genes. As for BA1 minor allele frequency cutoffs, we generally followed the Hardy-Weinberg principle to determine these cutoffs, and that was based on the expected prevalences in populations for each of these genes. Those cutoffs can be seen in the right-hand column here for each of the gene-disease relationships. And for those genes that have both recessive and dominant inheritance, you'll see that the recessive cutoff is generally or much higher compared to the dominant cutoff, as those variants will be more frequent in the population in potential heterozygous carriers of disease. PM2 supporting also generally requires absence in nomad, allowing one observed allele consistent with the SVI recommendations was what the VCEP specified. Exceptions for PM2 supporting and that general rule include the autosomal recessive gene disease relationships that we've specified, where those cutoffs are specified as shown below. And for Nebulin, one allele is still allowed while potentially going above that initial threshold if there's only one allele observed within nomad. Also, I should mention for genes with multiple mechanisms or modes of inheritance, those being again RYR1 and ACTA1, when the mode of inheritance is unclear for any given variant, our recommendation has been to go with the more conservative cutoff generally. As for PVS1 specifications, we have determined these based on general, again, SVI recommendations for PVS1, but we've also further specified regions that were set as critical based on published literature, as well as the most 3' downstream pathogenic and likely pathogenic loss of function variants that have been observed in each of these genes to determine potential areas where we could increase the score of PVS1 accordingly. And that was the case for the C terminus of ACTA1 for autosomal recessive inheritance or autosomal recessively inherited missense variants or loss of function variants, excuse me. And then for Nebulin in the C terminus as well, was indicated to be a region critical to protein function, and that was again the case for MTM1. Additionally, within Nebulin, in-frame deletions, particularly in exon 55, were deemed to be deleterious and critical to function. And so we upgraded any such variant to PVS1 strong as opposed to the default. We also upgraded 4 variants in C terminus that were deleterious, truncating or a frame shift that led to premature truncation. Those variants would be upgraded to PVS1 strong. And finally, for RYR1 and autosomal recessive inheritance, we specified that variants in the poor transmembrane domain critical to, or rather that domain was critical to function, and any in-frame deletions or exon skipping in those exons should also similarly be upgraded to PVS1 strong. This is a general, just summarizing visual of all of the criteria that we've specified across all of our genes. We created disease level specifications for 54 codes within the ACMG AMP criteria, and there are brief descriptions of the pilot rules set included here in that image. Codes outlined in black follow the general ClinGen SVI specifications, and for more information, the link here will show those general guidance or those general guidances by the ClinGen SVI. As for the pilot variants that we curated to test these rules, we looked at 87 total pilot variants across the 5 genes within the VCEP's initial scope, and those were classified for RYR1, there were 21 variants. For ACTA1, there were 30 variants, and those were the genes with the most frequent variants in the literature, at least. And then there were slightly less available, as can be seen for MTM1, DNM2, and Nebulin. And so those were our truth set of 87 pilot variants to test the specifications against. This was the general clinical significance within ClinVar for each of the genes that we were specifying variants within. In total, we had 28 pathogenic variants, 13 likely pathogenic variants, 16 VUS variants, 6 likely benign variants, and 24 benign variants, for a total of, again, 87 pilot variants to classify with these specifications. And then using these specifications, these are the changes that we saw across all of the variants that we were using as our truth set. Generally, the benign and likely benign variants that changed classification were just primarily due to frequencies in nomad and how those fit in with our updated specifications. VUS and likely pathogenic variants that were upgraded were largely to our assessments of PS4 and PM3, which we again structured for the rare nature of disease so that fewer but well phenotyped cases could result in stronger scores for PS4 and PM3. And so that again led to the upgrade in some cases for VUS and likely path variants, and likely pathogenic variants that were downgraded were generally downgraded due to conflicts within ClinVar, where a given variant was scored as pathogenic or likely pathogenic due to internal case literature, and those cases in aggregate with the cases in total that we reviewed for each individual variant did not have enough case level data with specific phenotypes to justify the pathogenic or likely pathogenic classification within ClinVar. So that led to the general changes between each of these categories following our specification and pilot variant rounds. Where we currently stand is again in a phase of sustained curation where meetings are on the second Monday of each month. We're averaging about 19 members per meeting, and we've so far curated or have in progress 25 different variants, which we've prioritized using the VCEP variant tracker. And those are all variants that we've reviewed since piloting the 87 variants, the 87 pilot variants, I should say. Challenges so far through this sustained curation period have included presumably path and likely path variants, often again being rare, which can make aggregating enough evidence to classify accordingly with what would be assumed a pathogenic or likely pathogenic classification a challenge. And so far, internal cases that experts on the panel have been able to point to has been very helpful in trying to aggregate all of the data for these rare variants. Some discrepant classifications in ClinVar are also more challenging to parse out based on multiple gene disease relationships, which can make prioritization of variants a slight challenge. RYR1, as Ozge mentioned, has been classified as definitive in relation to susceptibility to malignant hyperthermia 1, and DNM2 has also been classified as definitive in relation to Charcot-Marie tooth disease. And so a variant in either of these two genes may be conflicting in ClinVar and populate on our variant tracker sheet. But due to classifications for both disease assertions, that is the origin of the conflict. And so this ultimately can sometimes pose a challenge when prioritizing variants that have medically significant conflicts related to congenital myopathies specifically. In summary, again, we have publicly available specifications for ACTA1, Nebulin, RYR1, DNM2, and MTM1 at the link provided. Also, if you go to the Congenital Myopathies VCEP page on the ClinGen website, you can access these specifications from there as well. Next steps for the VCEP include continuing sustained curation as we currently are, and we're currently working on publishing the variant specifications and the pilot variants that we've reviewed up until this point. With that, I believe that's all that I have for today. So thank you everyone for listening.
Thanks so much, Ryan. Thanks to both of you for great presentations and a really productive set of expert panels. I'll open it up to questions now. Feel free to stick them in the chat or unmute or raise your hand and ask questions. Okay, I think that was really clear set of presentations. So I think if no one has any questions, and we had some really interesting learning about the challenges in a different disease area, then I can let you all go. And thank you so much, Ozge and Ryan, for presenting on all of the good work.
Thank you.
Bye all.
Bye.